So I guess we're here to talk, Rudolph and I talked about the CRISP project, and Rudolph, as a chief architect, is going to lead off, and then I'll follow up at the end. Go ahead.
All right, I'm going to grab this microphone, because I might walk around a bit. Can you guys hear me through this, or no?
Oh, I turned it off.
Oh. Okay, now it works. Cool. So, how does this work? Oh. Okay, so AI in medicine, AI in radiology. I kind of want to say the problem is much more than AI. It sounds maybe heretical in a workshop about AI. It's also a lot less than AI. What do I kind of want to lead into? Well, first of all, before I forget, I want to give a shout out to my team back at Children's, because I would always forget. Sandeep, who's on a lot of the pipelines we're going to see, Gideon, the UI front end, Jennings, a lot of the core infrastructure on OpenShift with Helm charts and amazing visualizations, and Jorge with all of the back-end databasing. So, okay, good. I did not forget to do that. All right. Without a fully deployed, a fully functional end-to-end deployment, no kind of computing, AI or otherwise, is really going to make any difference. So I've been in what I'm going to call scientific computing for, well, my entire career. I don't want to date myself. I did my PhD about 25 years ago, a quarter century. And it was in a field called reinforcement learning, which is one of the islands, right, or the continents in the ocean of AI. I'm going to try and wax lyrical. You'll forgive me, I'm going to put AI in quotes a lot of times in my talk, only to highlight the fact that AI is much more than just neural network-based models that everyone is excited about today. There's a whole field. In fact, computing is much more than AI as well. And I sometimes wonder to myself if people think computing just poofed into existence with ChatGPT. That before ChatGPT, computers did nothing. They just did email and Excel or something like that. But in my field, in scientific computing, software has been making changes for my entire career. I would even say 50 years ago, in the 70s, there were amazing software programs that were doing amazing things. So medicine is no exception. And I think the question that I often come back to is, why haven't we seen this amazing software make its way into medicine? I loved Eshet's talk, especially the first part when he said in 1995 there was a pseudo self-driving car that could, get 98% of the way coast to coast. 1995. Not only has technology been around for a very long time, but it is very rarely used. So I think part of the problem that we should talk about first is what is AI. Before we can talk about AI in medicine, we need to talk about what is AI, what is computing in medicine. And more to the point, what is computing in radiology? Radiology is probably the most digital of all the medical disciplines. And I'm going to give a spoiler, it is not that sophisticated. It is shockingly unsophisticated. And I think this is a huge problem, or a huge barrier to adopting a lot of these technologies. So in medicine, in radiology, we have these amazing devices. This thing costs probably upwards of $3 million, this MRI machine. It has a ton of computing on board to do its only one function, which is to make a picture. It's like a glorified camera, right? And all it does is it stores its pictures in a database. And all humans do, or radiologists, is they sit in these darkened rooms for hours on end on these huge monitors looking at these pictures, and they crunch them with their human brains. That is the totality of radiology and computing. This is what has to change before any of the stuff we're talking about today in AI could make any kind of difference. So let's do a little bit of a quick schematic around that. We can just draw this. Here I'm going to make, in the middle is that thing called a PACS, a picture archiving and communication system. That is the central thing. That is around which everything orbits. And this is what vendors charge astronomical amounts of money for. And all it is a database. That's it. Right, there might be tons of VMs around it and backup and bespoke machines, bespoke PCs that interface with it. But make no mistake, at the end of the day, it is just a database. So let's put a pause in that. and talk about what we're trying to do with this thing called CRIS. So CRIS is something we've developed over the last couple of years. It's a platform for scientific computing. Kind of bringing it to the cloud, if you will. And it's a long-standing collaboration with great folks at Red Hat, at BU, at Northeast, and generations of students. Far too many people to give a shout out over here. But at its core, it's about scientific computing. Now, I've highlighted that over there because that is the angle at which I want to come in to talk about AI. So, in the so-called CRIS way, all kinds of computing, including AI, run on the cloud in the same way as they would run on your laptop. And that might sound self-evident, but it's really not oftentimes how these things are deployed in a lot of large offerings with MLOps and DevOps. There's a huge change that has to happen from what a scientist like myself would write in the beginning and how it exists out on the cloud. And because of that reality, that's one of the reasons why we built CRIS, so that you as a scientist can run your thing on the cloud without having to rewrite it in fast API or put in a Python Flask or put HTTP requests around it. The kind of thing that scientists will never do. I've been around scientists for 25 years. You're dreaming if you think they're going to make a REST API call in their Python code. 1 or 2 might, out of 100. Most of them just want to write their app, read from files from the file system, and write files to the file system. That is how we do most of our science. So, there are exceptions. What is scientific computing? I'm going to just skip over this slide and go to the next one because it's a bit more practical. But key points, scientific computing is always batch processed. I've never written a GUI in my entire life. Everything is CLI driven. Everything is a whole bunch of programs that you duct tape with spit and a prayer in a bash shell script, right, to do its thing. We wanted to change that and make it more portable and make it available on the cloud. Oh, and importantly, although it goes without saying, this is almost always some kind of Linux-based, sometimes Mac OS. I haven't really seen anyone doing anything else outside of those 2 environments. But let's talk about computing in science, and this is actually how we do computing in AI. I will have a program, I'm going to call it analysis.py, that I've written maybe with VI, well these days I use NeoVim, but I wrote it straight up, it does its thing, and I run it always in a terminal. I might go to a directory, I might do a quick look, and I have my input and output data sources. And this is how all of our science is done. Inside my input directory, I have a whole bunch of files, there's nothing in my output directory, and I'm going to quickly activate my environment, and I'm going to type in a command line expression to run this analysis. And it will do its thing. It'll crunch, 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 and spit out an output. Everyone that I know in this field programs like this, and they work with these kind of models, quote unquote. Now, this is exactly the same in AI. If I was to do AI, like a training algorithm, I would write a Python app that consumes information from an input directory. It does whatever it's supposed to do, and it spits out, 9 times out of 10, a weights file. This is not a model. These are the tuned parameters for the model that only exists when my Python file is running. If I want to use this, it is just a program. Again, input, output. I'm kind of belaboring the point here. But this is how you would use it. You would read in the weights, you would read in your pictures, and your AI will do whatever it was supposed to do. And now it's done. It's finished. If I was a scientist, I would maybe analyze my output log file or the results to do a paper, to do something else like this, whatever the case may be. And let's look at how well this particular one did. Let's clear the screen. That was my input picture. And what did my AI think? Oh, well, it might need some more tuning. The point here is that, to me, AI is no different to any of the other scientific programs that have been staple in the field for a quarter of a century. It doesn't need anything special from my perspective. What it does need somehow is to bring this way of producing software to the masses, if you will, but to the web at the very least. So let's circle back, computing and radiology. So again, I had this picture. This is the be-all and end-all of radiological computing. And we can run this thing entirely right now on NERC using completely open source solutions. So here I have Orthanc PACS server, which we've deployed, containerized, thrown it out on a Helm chart, it's running. Orthanc is an open source product that, let's see if I can click on it. Okay, I don't know how to get out of this view. All right. Oh, okay, turn around and see it. So Orthanc, anyone can download it. I've seen Orthanc embedded deep within commercial offerings from huge healthcare companies in the US. It's certainly industry grade. Let's go back. Oops, where's mine? Clearly there's user error. How do I get back to, I'll do this. All the way to the right on my screen. Oops, there's that, to the right. To the right, to the right, okay. Can you see it? Okay, all right, this is a bit of user error. I'll try not to do this again, because how do I get back to my first tab? Alt F1? No. Oops, sorry. Come on, come on, come on.
There it is.
Okay, there it is. Okay, so I'll try not to leave that, and I'll have to go back to slideshow. Okay, all right, sorry. Okay, I'm going to stand over here or something because it's not on the screen anymore. All right, so there's also a viewer, right? Radiologists live their lives looking at these things, an open source viewer from the Open Healthcare Foundation based out of Mass General. We've also thrown this on NERC, containerized it on a Helm chart, it's running out there. And we can now, I'm going to have to see if I can do this, click on there. And here we see, this is, I just want to go full screen. This is a viewer right now on NERC that is good enough, I would say, for radiology purposes, full screen. All of this data is anonymous or public. Anyone, well, you need the login, right? But in theory, anyone can interact with this data, take a look. Here is a typical image of a real anonymized CT scan of lower legs, which is going to be used in one of the pipelines I want to show you. Here is a problem, right, that exists in radiology today. I just want to know if those legs are the same length. And that's it. I just want to know if they're the same length. Why? Because if they are not the same length, there's probably something wrong. But today, and Ellen can speak to this as well, a radiologist will sit in front of a viewer like this and hit these tools and eyeball where this joint is. I'm not going to do it. They will choose a measurement tool in the UI, pull it down to where the knee is, and it will actually give the length in centimeters. And they'll write it down on a piece of paper. Rinse and repeat for all of the 4 parts of the legs. And then they'll quickly add them up, maybe in their heads, maybe in their phone, I don't know. And then they will see if they're the same length or not. This can take 5 minutes, 6 minutes, if you're tired, even longer. I think we can all agree, we don't need a radiologist to waste their time doing this. This is something a kid could do. This is something that, wait for it, AI can do. Right, so going back, I can just learn how to navigate this thing properly. Where's my? All the way to the right. There, okay. I'm going to try and keep that to a minimum. Okay, so let's do a quick real-world check-in, shall we? Because this is important as well. And this is not about AI even, but it's the real world. I just showed you we did radiology on the web, on NERC, and that was the totality of it. If you were a rural hospital, let's say in South Africa, I'll pick on South Africa because I'm originally from South Africa, hence the slight accent. So if I was a rural hospital in a province in South Africa, I might have $10,000 US to spend on IT infrastructure, right? What I just showed you, a commercial package at a Boston hospital, costs about $3 million. But for 10K, I can buy 5 or 6 Dell PCs. I say PC. You wipe Windows, throw Linux onto it, throw OpenShift onto that, a Helm chart that I've just shown you, and wham, you have radiology on-prem on a cluster. I could use NERC, and the numbers might be a little bit higher than that, but let's say monthly cost of 200, maybe a bit more, maybe double that, let's say 400. It doesn't really matter. The monthly cost at a Boston hospital is 25K for that. My 10-year running costs, maybe another 10K over 10 years for my provincial hospital. NERC will be 24K over the 10-year period. 3.6 million at a Boston hospital for the 10-year running cost. After 10 years, my provincial South African hospital has spent 20K to have the same basic technology that Boston Children's Hospital would have at 6.6 million. There is no way that a provincial hospital is going to spend 6.6 million on this infrastructure, but they for sure will spend 20K on an in-house cluster. They can do this. If I say nothing else, if I end my talk right here, and I close the laptop and we're done, this will change radiology much more than anything else we're talking about today. Just this one slide. But, of course, I want to talk about it a little bit more. So let's combine these things together. That's the picture. Computing and science was this little blob. So what we do is we hook chains of this computing, firing off the PACS that lives there. Now, the commercial PACS I showed you in the previous slide has no capability to do this. But on NERC, on OpenShift, you are able to hook these things together. You are able to leverage data in one resource, pull it to another, and build these chains of computing. The database that these vendors spit out cannot do this. And if you've spent 6.6 million on that, you're going to be very reluctant to change that infrastructure. And of course, you need a little bit more. You have this whole infrastructure, which is part of CRIS as well. I wanted to highlight with that yellow or orange circle over there. Let's call that AI, right? If you want to. Without all those other circles around it, that orange circle is again meaningless because it needs this infrastructure to give it the right data, to convert medical images from one format to another, to convert them back, to put things around, yada, yada, yada. We all know the story. But this is oftentimes overlooked, I think, in the excitement of showing how great some of these bespoke computing things can be. Without the rest of it around it, you almost might not bother, except from an academic perspective. Okay, so I'm going to now shift to another tab and just show you some of these things very quickly. I'm going to show you let's start with the brain tissue segmentation, because this actually touches on the previous point, I think, that Esh had mentioned. Oops. But while it's rebooting, we might not be able to see all the nifty things we put together. I'm going to try very hard, depending on the time. And I want to be respectful for the next speaker as well. I was going to, at the end of the talk, say everything I'm about to show you, you can see right now yourselves. So maybe we should do a group thing here, perhaps, those of you with computers. Right now, you can go to the following URL, app, like app.crisproject.org. Those of you, you can do it on your phone. That will be a good test. That will take you to our CRIS instance user interface out on the web, out on NERC. And it'll take you to a public set of feeds. We call them feeds. You should see a table. And there should be one called Free Surfer. And if you click on that, you will see, it'll go to another display, and you will see this chain of computing, kind of like I showed in the previous slide. And those are the actual containers that have been strung together to perform some kind of computing operation. And one of those, I'm trying to think which one it is, says segmentation. And that is the one that actually takes a medical image and does volumetric classification. It takes a brain and figures out which pixel belongs to what tissue. And once it's done that, you are able to figure out stuff like, what is the volume of these structures? Are they growing? Are they not growing if you do repeated measurements? That Free Surfer, and full disclosure, I used to work with the Free Surfer team again years ago. They're based out of MGH. That does not use AI at all. There's no AI in that, just straight up statistical heuristics. It takes a long time to run, though. It takes about 10 hours. But it was doing this 25 years ago. But this entire infrastructure of computing and radiology, which is so geared to not allowing you to expand out upon it, has prevented a lot of these very useful tools from coming from the bench, from the research bench, into the clinical side. Now, there's another one of those feeds. It's called Fast Surfer. That is the Free Surfer with AI, and it will give exactly the same results. And that's kind of an interesting point, right? We tend to think that AI is going to give us stuff that we've never seen before, but oftentimes its most useful aspect is it can just give us the stuff we already need just a lot quicker. So Fast Surfer has been trained off free surfer segmentations, and it is able to do the same segmentation, but it takes about 5 minutes, while Free Surfer takes about 8 hours. But Free Surfer never made it into the clinical workflow 25 years ago. And we would be optimistic if we think that this AI version of Free Surfer will make it into the workflow just because it's using AI. I think the playing field needs to be rethought. And I think almost innovation is actually going to probably also come from places where they can do their on-prem OpenShift cluster for 20K, hook up their stuff, hook up this infrastructure, and begin to innovate on that as well. And, okay. Okay. All right. So this is the public CRIS that you guys can all see. You can even create an account if you wanted to. If you hit the plugins, you will see a list of all of the compute that we've made available already on this public interface. These are all containerized applications. Most of them are not AI, but you need all of these to make any kind of compute workflow meaningful. The new and existing analysis that I wanted to mention over here is a Fast Surfer pipeline. So this would hook up into that database that we're running on NERC. It will pull the data out, and then it would be able to run this kind of predefined computing workflow on that. This node over here is the actual node that contains the AI-generated results. And if I go to it over here and look at one of these, for instance, one of the segmentations, it will pull it down from NERC into our preview window over here. And it will show the segmentations. I'm just going to do this, put it into Free Surfer colors. So this is a brain that has been pushed up, the image is pushed up to NERC, pulled into our system, analyzed, everything has been classified and has been pushed back into the radiological viewer. The example that I showed wanted to show about the leg measurements. If you just go, this is a custom UI that is sitting on top of our system. Behind the scenes, all of those circles we saw are busy running. Now it's pulling an image from that workflow. It is running a scan across it. It's using AI to find where those joints are. And then once it has found the joints, there's a whole bunch of other computing that then goes and measures these lengths and actually draws onto the image a report, which we'll see now. It should be coming any second now. So those are the landmarks that it has found, and there's the report. And now it's pushing it back to the PACS interface where a doctor would look at it. So this can take a few minutes to run. By the time the patient has been scanned, it can be pulled automatically into our workflow. It can push results back into PACS. By the time the physician sits at their display, the data is there for them. And if they are okay with where those landmarks are, it takes a second for you to run your eyes and say, I'm cool with this, then you can trust that the measurements are correct. Within 1 or 2 seconds, you know if these legs are the same length, as opposed to painstakingly doing it for 5 minutes manually. All right, so I think I'm going to move on, and that's the end of my part. And let's do this.
Great. All right, and just wanted to point out that little, whoops, I'll put it in the slideshow, the little orange box that Rudolph was showing with an algorithm. There are so many algorithms like that we need in our clinical workflow. And the problem is if we buy each one of those from a different vendor, we just get overwhelmed by the amount of devices trying to connect to our PACS system. So it's impractical. Plus, when you work in a field where there's not a lot of people that have, say, the computational infrastructure that we have, or the people with talent such as Rudolph, you don't have people to write those algorithms that you need for the physicians at your hospital. Another example of these algorithms that we need is we do a lot of fetal imaging because we're a major fetal surgical and interventional site. But when you're imaging a fetus, their head moves, as you can see here, as you're imaging the fetus. So as a result, the images that I get to read are all this mishmash of angles in different directions. And so we keep chasing that fetus, trying to get it in the right angle so I can do a clinical interpretation and hope I don't miss anything. And we'll do it maybe 10 times. So I have 10 stacks of 15 images each that I'm working through, trying to put it all in my head and making sure I don't miss anything. And that takes a lot of time and a lot of mental energy. So we've worked with, this is an algorithm we've done with MIT, and you'll see it starts out when we get to the 0 as blurry, because we put all those images together into one coherent volume, and then we jiggle them to get them all coherent. And so we can, and this particular algorithm, which is actually an AI algorithm or a machine learning algorithm, runs in, you see, just a couple minutes. So I can take those images, and as they're being pushed to the PACS, they're being analyzed, put into a coherent volume, and then pushed back to me at the monitor, so I can actually read one coherent volume instead of 10 or 15 stacks of images that are in random oblique orders. So this is something that we're really excited about and have automated most of the pipeline on it, and we're going to make that available on NERC. And this is where NERC becomes important. We have this, but all the other sites that I know of, at least in the US, don't have this because they don't have the infrastructure. But we can share, and we're working on doing those kinds of sharing. Another thing, because we do a lot of fetal surgeries, we want to come up with more innovative ways to assess fetal well-being. And it's really hard with ultrasound to do that because the fetus, you only see a small piece of it with an ultrasound beam, so you can't get that global look on what the fetal anatomy is or on the fetal motion. So these are images that we've done, they're volumes that we acquire actually through the pregnant abdomen and use machine learning strategies to track key points like elbows, shoulders, knees, hips. And we can track fetal movement over time and create these videos of what that fetus is moving like. And also I can get real metrics on how that fetus is moving. And why is that important? Well, I talked to you want to understand the fetal health and well-being, but we're also working with a lot of surgeons at many different sites around the world that are part of this North American Fetal Therapy Network. One of the main therapies that's happening now in utero for malformation called Chiari-2 malformation, or a spinal cord, a defect in the spinal cord here, the skin of the spinal cord, is that in this defect here, you can see this elements of the spinal cord get exposed to the amniotic fluid. So the skin and the bones are not over top of it. So you have a sac with neural elements in it. And as a result of that, there's injury to those neural elements that decrease movement of the legs and feet. So what we do, and what is now standard of care, is the surgeons will operate on the fetus. This is the abdomen of the mother opened up. There's a little sac you see right here. And then they've closed it and put it back into the uterus, and this is after delivery. This is currently the best way to improve the outcome of the motor function of the lower legs. So what we want to do is continue to help these surgeons innovate on improving strategies for surgical management of this patient population. And here's an example of the movement of a typical fetus versus one that has a sac that's fairly high in the spinal cord, or spinal back of the spine. And you can see that the movement of the legs is much less and less of a range of motion than on the typical fetus. So now I've got numbers that actually can characterize that fetal motion, say how do surgeons do at our site versus other sites. Okay, we want to tweak the approach just a little bit and see if we get better outcomes. I can actually track after surgery, how does that change fetal motion? And it gets really important because the only way we do it right now is just look at how their legs and ankles are moving. And typically, as the fetus gets bigger, their movement decreases, so that you can't regress out normal. But now that I've got data, I can regress out normal motion and give them more accurate feedback on whether we're making improvements or not. So in pediatrics, we have many disorders with small numbers, and so industry is not interested. And I think that happens in a lot of different areas in medicine. So there's a need for a community to share images and like from multiple sites that I showed you from these surgical centers, and to develop and share tools. And that's what we're really excited about NERC and the CRIS infrastructure, is we can say to now all these sites around the world, you can have your private enclave in this environment. Here's CRIS, go to it, go analyze analyze their data, use our tools, and we know it's going to be reproducible in terms of its performance on their data. And we work hard to harmonize the data acquisition strategies as well, too. So it kind of makes a community for us to work together and do really good science on how to improve medical outcomes.
Oh, all right. So quick take-homes then. We have built this infrastructure already. Today, it's running out on NERC. Those public feeds that you saw is what we would like to expand out to show all of these additional processing that Ellen just mentioned. Those public feeds, you can actually download the computing as well. It has links to the containers, or you can instantiate your own CRIS on your own laptop and just run them straight up for about 1 or 2 clicks.
So as you've seen, like solving problems, particularly in this century, we have to work together. I think that's true in adults, but even more so the need is in the pediatric populations. We need to work together across centers and bring data from multiple sites together and have a place that we can connect and bring all the data together to allow analytics on these data and to share our algorithms in a way that's easy to use. So for example, some of the sites here we work with are in Europe, and they don't have a team like ours. They can't even, it's really challenging for them for downloading an algorithm and set it up in their environment and run it on their data there. Here with the CRIS infrastructure and with NERC, we could actually set it up. They could do it like that, and it's no problem for them to be on the same page as we are in terms of access to algorithms. Sort of similar to what you mentioned before, Jeremy, about having 3D ultrasounds available to a rural community. A rural community could, upload an algorithm. It could be a chest X-ray, and we could have an algorithm that automatically takes the ribs away, so you can look a little better and see if there's anything hiding behind the ribs. There's so many algorithms that are out there that we could put in this environment that low and middle income countries, small rural communities, as well as hospitals and other sites around the world could have access to.
And then the final thing when the rubber hits the road, again, the real world for us, at least in this field, is that there's this thing called HIPAA, which is the compliance regulatory infrastructure for any kind of sharing. And it's kind of the missing piece right now, I think, with NERC. If NERC were to be HIPAA compliant or have that title, then a lot of these other sites that I mentioned over here, these hospitals, their biggest resistance or barrier to wanting to take part would go away. And then we will be able to begin to fully connect these things together and begin to build this true open science, open source kind of medical processing environment.
Great, thank you. I don't know if we have time for questions because we're running behind. Should we see if there's one? Jonathan.
So, of course, just amazing, especially since I've had a chance to see some of this over the years. So a couple of questions, but one, could you put back the chart of the cost chart just as a backdrop to the question?
It's near the beginning. Okay, that was a bit of a thumbs suck.
Oh, that's okay, that's okay.
As I'm not a...
That's okay. So a few things. First off, I was, throughout the talk, I was thinking about this last point you brought up, the HIPAA compliance. And I was thinking back to a class I taught in 2009 when I first got here about cloud computing. I invited lawyers to the class, and they said, hey, look, it really doesn't matter. Don't look to us for guidance. You do it, and society will force us to legalize it when it comes down the pipe. And that stuck with me because in the same way of what you've done, it's something now that society can actually engage with, see. So, because now you've demonstrated that, look, government organizations and legislators, it's all otherwise abstract, or they end up hearing a lot of BS from people in companies wanting to talk to them about what is not possible. But here there's an actual data center. There's a place to actually put numbers up and say, look, okay, you decide. Do you want to donate this amount of taxpayer dollars to save these lives or not? So I think this is just if nothing else, raising the bar of how the conversation engages is phenomenal. But now, actually, one of the things I was curious about, in terms of these costs, if you had your way, because I'm very curious about this cost trade-off to running it locally, what would you want to see go down in cost when it comes to something like a cloud platform? Do you have any sense of what you would want?
I guess my first want would be storage, because if you there's so much we could put, like we have lots of normative data that we share as well too. So be able to store data on the cloud and not have to incur large costs for storage could create an environment where people will come. So if we've downloaded probably 15, 20,000 data sets from around the world that are normative, for example, and we enrich it locally, we create teaching files of exemplars of unusual disorders. So having a place that you could put it where people could access and not incur a large cost, because I don't think the processing is a lot. It's more, where do we put the data and how do we make that feasible? And I think when you're doing it with multiple sites around the country, we don't have to necessarily store their data there. It can be a transient, upload, analysis, download, and then wipe it out. But we still, even if that much we could get HIPAA compliant for a transient, would be a huge step forward. What are your thoughts?
Yeah, I mean, cost, money makes the world go round, right? I mean, let's say NERC, here I put 200. You can double it, maybe make it 48K over 10 years for a couple terabytes. Make it 100K, right? It's still going to beat a bespoke commercial enterprise sitting at a place like, Boston Children's. I don't know if that cost, in that space, I would see the competition more with other cloud providers. What does Amazon provide? I don't fully know. One of the guys on my team told me, Amazon has this data something for open science where they give you free access, which sounded like news to me. I don't know if anyone else knows about that. But I'm reluctant to want to put anything like this on a commercial company like that. Amazon, you suck your data in. How are you going to get it back out? So the costs are important, but also what was important to me is also the fact that, and to maybe collaborators, is that you can put your data in and you can download it. There's no lock-in at all, right? I think that's super important.
Yeah, I totally agree with the egress. Like, we need to put it up and get it back down, and the data governance structure is something, frankly, I think from a hospital point of view, we'd rather not have industry overseeing our data, because you never know what it's going to do with it.
Right. And just one more on a technical front on the cost breakdown. So I really, your general approach to warning us that AI is not the most important set of letters in these statements when we talk about making computational useful. To that end, you did point out that a particular AI version of FreeSurfer was able to be faster, right? Now, I was curious, when we consider the belief that NVIDIA is going to rule the world and GPUs are the way to get that win, I'm curious how these cost trade-offs, like, were you assuming that on that local install it was GPU based, and how do you run on the NERC side? What do you think of with respect to the GPU usage versus the CPU usage?
Okay, so that's a funny story. I mean, I don't know how many folks in the audience actually use TensorFlow on different GPUs and try to get things running. I want to say it's a shit show. It's really hard. So the stuff I've shown here aren't actually running on GPUs. They're running on Intel with AVX extensions. And it's not as quick, right? But sure, I'd be willing to have it run in 5 minutes and know it will run everywhere than have to maintain these 5, 6, 7 different 8 permutations, the same code base for different GPUs that maybe run in 20 seconds. It's just not worth it. So I don't know if that answers your question, but yeah.
For the next person.